When we consider using cos and sine graphs as building blocks for modeling, we looked at this form here where we had a vertical scaling and shifting and horizontal scaling and shifting as well. We're going to focus on the amplitude factor, the b value there. As an example, let's take the graph of y equals 5 of cos of x. Now we know what the amplitude means. It means that the graph, if its cosine starts at its peak, it's going to have an amplitude of 5, so we go up 5, and then we're also going to go down 5, and then we're going to go up 5 to 0 and back up to 5 like again here, and repeat like so. And the graph will look like this. I'll get rid of that extra point, and we keep going. That's x, and because there is no horizontal transformations, the period is the natural period of the cosine graph, which is 2 pi. We're going to add something just about the 5, and notice we have the absolute values here. So the absolute value of y is equal to 5. That can happen two different ways. It can happen with y equals 5, or y equals negative 5. And these are both horizontal lines. If we find all the points where y equals 5, well, that's all these points here, that would be this horizontal line. We also have all the points where y equals negative 5. Now, why do we do that? Well, if you think of what happens with cos, it goes between the cos part by itself. It is always going to be a value between -1 and +1. Well, that's what, when we scale it by 5, we get then as a maximum value being 5 and a minimum value being -5. And so in some sense, this absolute value of y equals 5, those two red lines, define the boundary for the curve of 5 cos x. We can go up and down in between those two lines, but we're never going to exceed it, and we're always going to just come up and touch it. Now let's make things a little more interesting. What if we now put a variable, not a constant, not a 5, not a 10, not an 8, but an x in front of this cosine graph? Let's see what that looks like. We're going to use our inspiration from the last page, which said we should look at the boundary graphs, which would be y equals x, or y equals negative x, that would be the negative absolute values. And for scale, let's make this 1 and 2 and 3, 1, 2, and 3. Connect those with a straight line. Likewise down here. If we had the vertical scaling, 1, 2, and 3, and -1, -2, and -3, our inspiration would be that the cosine graph is going to have to stay within these boundaries, because cosine is between -1 and 1, and we're going to multiply it by x to the biggest, so whatever happens, we're never going to ever get bigger than x, and we're never ever going to get smaller than the value -x at any point. The other issue here that we have to take note of is cos of pi x by itself has a period of 2 pi over the multiplier because it's compressed, and so a period of 2. How does that play out? Well, we're going to finish one full cosine cycle by 2, and cosine cycles end at their peaks, and in the middle they're at their negatives. So we can actually quickly come up with a sketch of this much more complicated function because of the non-constant amplitude. We'll notice that in between or on the half periods in between, we're going to have 0 values for sure, because when cos is 0, it doesn't matter what the x is. So the zeros are going to stay the same. And we're going to get this interesting looking graph here that has a variable amplitude as we move from left to right. The graph of y equals x cos of pi x is going to have this increasing amplitude shape, and the way we can define how large those amplitude waves are is through this little trick of looking at the amplitude as a function, drawing that function, there we go, y equals x, and its negative version, y equals negative x, and using that as the boundaries for the curve. Let's get a little more exotic. Let's try e to the x. And again, remembering what the boundaries will be, if that's our amplitude function, the boundaries will be at y equals e to the x and y equals e to the negative x. Let's see what that looks like. Well, if we have a function, let's start at 1, 3, 2, and let's make this a little bit larger period here. All right, what does e to the x look like? Well, e to the x starts at 1. When we get to 1, we get e to the 1, which is around 2.7. And by the time we get to 2, it's like 9, so it's way off the charts. Let's put it up here for argument's sake. That would be our e to the x graph. We could probably scale this better for the graph we have here, but starting at 1 here is sort of a natural place to begin. We would also do the same in the negative direction, like so. The period we had in the last page was 2. The same thing applies here. So what we know is that the graph is going to start at its peak, contacting the upper line. When it's halfway through the cycle of period 2, which is 1, it's going to be touching the negative boundary. When we're at 2, we're going to be touching the positive boundary. At 3, we'd be touching the negative boundary down here. But in between each of those points, we're going to be having a 0 value. We can check that out. We could plug in a half. Cos of pi over 2 is 0. Cos of 3 pi over 2 is 0. 5 pi over 2, and so on. What does this give us? It gives us, I think, a fantastic shape of this graph like so, where we get these massive swings of the cosine function because the amplitude is growing exponentially as we move from left to right. So we can get some pretty interesting graphs simply by being a little more flexible about what we mean by amplitude, not resorting only to constants, but allowing ourselves to use functions of x as well, and seeing how relatively easy it is, once we know the graph of the amplitude function, to sketch the actual graph of that amplitude times a sine or a cosine. It gives us a lot more flexibility for modeling almost periodic functions.